Okay, ladies and gentlemen, welcome to Aviation Weather by Kieno Thomas. I encourage you, if you don't have the book, get the book, Advisory Circular 006A, or just Aviation Weather. You can go to barnesandnoble.com, or you can get it used at eBay. I'm pretty sure Barnes & Noble may have some used copies too that you can buy. This book is, if you're a professional pilot, it is like a must-have. I've had this book for like a long time, and it's worth its weight in gold if you're a professional pilot. So last session we covered chapter 1, and we talked about the atmospheric composition. We talked about atmospheric pressure and density. We talked about oxygen, how oxygen affects, or oxygen deprivation happens when we get into the higher altitudes and we don't have supplemental oxygen. We talked about hypoxia. We talked about supplemental oxygen systems. We talked about the regulations that govern us if we're general aviation, corporate, or airline pilots, and how that affects us and as well as our passengers. And this is gonna segue right into chapter 2, which we're gonna talk about temperature. Temperature can be defined as I guess it's the degree of hotness or coldness or something. Here we had a guy on the left freezing here, and we got a guy on the right burning up. He's in a desert. So it's the degree of hotness or coldness or something, and temperature is very, very critical during some flight operations. We could have precipitation, rain, snow, sleet. We could be in a cold situation. The runway could get iced over. So we have to be able to, or we could have we could have a weather system coming in to our destination airport by the time we get there an hour or two later, and those conditions could exist. So I'm also going to do a video series on aviation weather reports and forecasts, but it is very, very important. So temperature is very, very critical. We could have things going on like in-flight icing. Well, the plane's on the ground, but it's iced over, and clearly this aircraft cannot take off like this because the ice is going to interfere with the smooth surface of the wing, and that smooth surface is how the plane was manufactured. That smooth surface is the perfect curvature to maintain lift or develop lift to keep that aircraft in the air in flight conditions. On the lower left, we can see the runway looks iced over and stuff. So imagine being very, very low on fuel, not doing and I'm talking about general aviation guys. Imagine being very, very low on fuel, not getting weather, not talking to a pilot weather briefer, and finding out that this airport was closed, and you fly there, and you're like, wow, I can't land there. I'm going to hurt myself, or even worse. But on the warmer side of things, as temperature increases, we need the air density decreases as the temperature increases, and we need longer runway because the aircraft is actually going to act like it's at a higher altitude. So less air density, we're going to get less thrust because as this propeller is spinning, the air molecules will spread apart because it's warmer, and you're not going to get the same amount of thrust. So you're going to need, and also the way that the air molecules strike the wing and provide lift and the deflective force for Newton's third law of motion to start developing that lift or pitching the nose up. So you're going to need a longer runway, basically. So in this video, we're going to discuss commonly used temperature scales, and we're going to talk about how heat and temperature variations should affect flight operations, like I mentioned before, on the ground, or we say surface, and up in the air, aloft. We basically use, in aviation, we use two different type of temperature scales. We measure things in degrees Fahrenheit, and you can see the F here, and we can see the C in degrees Celsius, or some people say centigrade. All right, so those are our two temperature scales. We could be on a Fahrenheit scale, we could be using a Celsius scale. So basically, when we look at this, the two common temperatures references are like 0 degrees Celsius, 32 degrees Fahrenheit is pretty much the freezing point. So at this point, we're going to start freezing if we have precipitation. If you get a winds and temperature off forecast and there's let's say rain, there's a low pressure system coming in and they're talking about thunderstorms coming in, and you don't have the proper icing equipment, you don't want to fly in that area. Now if your plane is equipped to de-ice, then okay, your aircraft is prepared. But for my general aviation guys, this is why we need to have a thorough knowledge of weather, so we don't get ourselves into bad positions. So basically at 32 degrees Fahrenheit, 0 degrees Celsius, pure water freezes and it boils at 212 degrees Fahrenheit, 0 degrees Celsius. We've talked about that. And that's the boiling point of water at sea level. We've talked about that. And we talked about that. Just cut ourselves off at the pass here. Alright, so the difference between our melting and boiling point is 0 to 100, 100, and then 32 to 212, 180. Now we could look at that as a fraction, because what we're going to do, or I didn't even put that in. Oh yeah, I did. Alright, so yeah, 100 and 180. If we reduce this to the lowest terms, we get a fraction 5/9, and keep that in mind because we're going to need that for a temperature conversion if we're converting Fahrenheit to Celsius or Celsius to Fahrenheit. So keep that in mind at a later time. The difference between 100 degrees Celsius and 180 degrees Fahrenheit. And then that breaking down into 5/9, because there's a conversion chart. So we talked about temperature. Now let's talk about heat. Heat is actually energy. It's a form of energy. Here we look at a bowl of soup. And sorry about that, that was my phone. I don't know if the video picked that up. When a substance contains heat, it exhibits the property we measure as temperature. Okay, so some substance it contains, think of it as like a house, it's housing the heat. And the property that it exhibits, we can measure is temperature. So we can stick a thermometer in this soup and we can find out how hot it is. Alright, and then we talk about the definition of temperature again. Alright, so a specific amount of heat absorbed by or removed from a substance raises or lowers its temperature a definite amount. So in order to get this metal hot, like it is, we had to add a lot of heat to this thing in order to get it very, 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 very hot. But water is very different. To get water hot, it would probably take less heat in order to raise that temperature. Same here, when this ice starts freezing over, it's lowering the temperature of the wing. So the amount of temperature change depends on the characteristics of the substance. It could be soup. Doesn't really take a whole lot. Well, it does take a whole lot to get that going. I think it will probably be somewhere above 212 degrees because there's water content, and then you have other things housed in it, the beans and vegetables, or you may have meat in there. So as a whole, but you would need a whole lot more heat to get this thing steaming and hot. So depends on the characteristics of the substance, the amount. And this is just basically saying the same thing. Here we have a guy ice fishing. This guy can literally hang out, sit on his thermos on top of the lake bed or river bed or whatever this is. It's probably a lake bed. Where these guys are fishing in the lake, they can't sit on the water like that because this water is warm now. The temperature has been raised. In this case, the temperature has been lowered. So it depends on the characteristics, and this is well below 32 degrees Fahrenheit or 0 degrees Celsius. And this water isn't exactly boiling at all. These guys could, well, they could swim in it, so it's not 100 degrees Celsius or 212 degrees Fahrenheit. All right. So, just to segue into this, and let me just back up, the amount of temperature change depends on the characteristics of the substance. In aviation, we talk a lot about the land or sand surface and the water surface, right? And so the ground actually radiates better than water. It takes a lot of heat exchange or heat, hotness or coldness in order to get water going as far as the temperature, moving the temperature. And strangely, with land, it's really not that hard. The same temperature is affecting the land here and the water at the surface. Okay, if we dug a hole in the beach, then that sand at the lower would be cooler, but we're just talking about the surface temperatures. So we would have to add a lot of heat to this water in order to get it hot at the surface, whereas we don't need that necessarily. A lot of people wear sandals. Sometimes when you go to the beach, it's so hot, it's like the sand is like burning your feet. You're like, ow, you know, you're kind of tiptoeing, and it's very hot, say, like especially at noon. So we're staying in line with the substance, and if we add heat to that substance, how the composition of that substance dictates how hot the surface is going to get. And so I show you hottest surface here, sand's burning your feet, and the cooler water, surface water temperature. At this point, you'd probably be getting the chills before you get in the water, and you probably have to put your feet in and then walk in till it's up to your waist, and then get your chest and your head in. And then after you adjust, then you're swimming and having fun like these guys out here. Or I think that might be a swimmer or person. So that's basically what I wanted to talk about. So, and when we add a certain temperature, when we heat the water and the land, same temperature, the surface or ground surface actually radiates better, or it radiates more heat. And conversely, if we freeze it, this is kind of like a winter day, no snow, but it's cold. The ground actually is colder than the water. So that's interesting. You'd think it'd be the other way around, but it takes a lot of energy to heat or chill water. Alright, so this segues into, okay, so where in the heck does this heat come from? Well, it comes from solar radiation. Here I have depicted, we have the sun, we have solar radiation coming in, and you can see the Van Allen belts, the magnetic belts here, and we can see the Earth right here. Okay, this is just kind of, I don't know why that's there, but it's a picture that I clipped. And don't be really concerned with that. What I want you to focus on is just the solar radiation coming in, and to segue into how we're getting all this heat, energy, to make things very, very hot or not so hot. All right, so the Earth receives energy from the sun in the form of solar radiation. The Earth and its atmosphere reflects about 55% of that radiation and absorbs the remaining 45%, converting it into heat. So there's different types of radiation, if you would. Think about your radiator. Your radiator kind of takes the heat away from the engine, and it just kind of emits it. That's why, you know, it's behind a fan. I don't know if you guys know anything about cars, but you got a radiator, and then there's a fan system to kind of blow it, and then you have coolant and stuff in there. So But not to go too far off tangent. So a lot of the solar radiation, more than half, is reflected. All right, and then 45 is absorbed. How is it absorbed, you might ask? Okay, well, that's that same sun. Solar radiation comes in, heats the ground, and this is called terrestrial. I was about to say terrestrial aviation. Terrestrial radiation. So, sun heats ground, ground heats air above it. Okay, and this is how we get air mass formations and stuff like that and everything. Because the intensity, depending on how high the intensity those sun rays are coming in, say like the desert, this looks like a desert situation. Depending on how strong that solar radiation is, kind of tells you how much the ground is going to reflect. Would that be the right word? Reflect or emit, let go of the heat. So sun heats the ground, ground heats air. Just keep it simple like caveman. Sun heat, ground heat, air. Alright. Now I just want to make sure terrestrial radiation. Alright. The average heat gain from incoming solar radiation is equal to the heat loss in order to keep the planet from getting progressively hotter. So although we get that 45% of solar energy coming in, a lot of the heat is let go. Okay, so that ground heating air plays a big part to keep things in balance. If that did not happen, the sun rays would just heat the earth and the planet would get hotter and hotter and hotter and hotter and hotter. Or colder and colder and colder, depending on the intensity of the sun ray or sun rays. Now, this is a depiction of the planet Earth, and we have the equator in the middle, the northern and southern hemisphere. And we know at the North Pole, it's very, very cold. We know at the South Pole, it's very, very cold. But there's something that I'd like you to pay attention to. What I'd like you to pay attention is to the heat balancing act that happens. Or this is one part of the heat balancing act. During or near the equatorial regions, say like Ecuador, or Ecuador, I believe, if I'm not mistaken, the equator runs through Ecuador. Very, very hot tropical region. Let me see. So this, the land masses in this are not kind of like true, but at any rate. And I could be wrong about Ecuador, don't quote me on that, but near the equatorial regions, one thing is for sure, is that this is a very, very hot or warmer part of the planet. And then at the polar regions, North Pole, South Pole, it's cooler. It's not as hot. And there's a reason why. Look at this incoming solar radiation, and look at the incoming solar radiation here. This solar radiation is really distributed over a very small area, and that's why these areas are so hot near the equator. Here, if you look at this incoming, because this is a curved surface or a sphere, this solar radiation is spread out more, so it doesn't heat as much like it does here, and that's why the equatorial regions are hot and the polar regions are cold. Right, and this plays a part in our regional and local temperature imbalances and stuff like that. And these temperature imbalances, and this is why we need to talk about heat, cold, hot, or heat, coldness, and temperature, because these are the main players or the gears that kind of drive the weather. We're right along, just checking where my time is. Okay, so there's a whole lot of things in addition to that. Our incoming how our solar radiation is distributed plays a part in our weather, and time of day, diurnal radiation is what we call it. That concerns time of day, seasons, the tilt. And I didn't put that in this video, but I'm going to do another video about it. But the Earth is tilted on its axis, and the Earth is spinning around the Sun. That's the theory, at least, and it works out because we could see this is the reason why we get different seasons, and it gets a little bit colder and a little bit warmer because of that tilt and the rotation around, not the rotation of the Earth, but the rotation around the Sun, and latitude. So longitude lines run vertically, latitude lines run horizontally. Alright, so all this stuff plays a part in the amount of solar radiation that area receives. Here, just going back to our incoming solar radiation, we can look at that. Remember, warmer at the equatorial regions, colder at the polar regions. Here are the polar regions, and we can see blue representing cold, and red or yellow representing fire, hot. Okay, so around here we get the very, very warm temperatures, and at the polar regions, because the solar radiation is distributed over a larger area, that's pretty much the major player in why these temperatures are the way they are. Okay, so the differences in solar radiation create different temperatures around the planet. We looked at that as well. And these differences in temperatures are the driving force that keeps the atmosphere in motion. The atmosphere is always in motion. It never stops. Alright, it keeps going like the Energizer battery. It keeps going and going and going. But we're going to talk, we talked about terrestrial radiation. The next type of radiation we're going to talk about is, or I would call it a variation, not radiation, diurnal variation. This is basically when the sun rises, things get a little warmer outside, if you notice. Around 12 noon, when the sun's in your areas at 12 noon, 12 o'clock high, lunchtime, we get very, very high temperatures, and then in the afternoon it gets cooler and cooler and cooler and cooler. Now, for you guys that aren't really that savvy with graphs, the T represents temperature. So this is midnight, 12 a.m., and it's like the temperature's still dropping, 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 dropping. Okay. 6 a.m., sun's up by this time, and the sun's up, and it starts warming. So this is what diurnal variation is about. The sun is starting its warmer process. In the morning, the oven is being turned on. Alright, let's just think about it. Your oven's being turned on at 6 a.m. And at first, when you first turn the oven on, it's not hot at all. It's not warm at all. Look at our temperature. So, just think of the day going by, and then let's check back at that oven. We don't want to stick our hand in there without gloves, because now everything in there is warm, hot. So at 12 noon, like I said, we get our maximum solar radiation, maximum incoming solar sun rays, solar radiation. And basically, at this point, the oven is turned off. Okay. Now, we have some convection going on, and we'll talk about that later, but the temperature actually keeps kind of going up and up and up and up and up. Why? Because the Earth is still radiating heat. Just because the sun ray is kind of like reduced, or we turn the oven off, doesn't mean that heat is not still there. If we stick our hand in that oven, it's still going to be hot. You're still going to, if you grab that pie, or I don't know, what do I bake? Salmon steak sometimes, or that steak, you pull that out, pull that pan out with no gloves, it's still going to be hot. And then around 3 to 5 p.m., the sun is setting, and then the temperature just progressively starts to drop, 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 which brings us back to midnight again. So that is temperature, our degree of hotness or coldness. 12 a.m., we got a temperature drop, sun rises at 6 a.m., and we turn the oven on. Okay, at noon, we get our maximum solar radiation. There's a lag. Remember, the Earth is still reflecting that terrestrial radiation terrestrial. I'm just working on my pronunciation of that. I can pronounce it, but I just get a little tongue-tied sometimes when I'm doing videos. And then around 3 to 5, then the sun's starting its setting and less solar radiation and the temperature drops. This represents, the time scale is the same, but this is solar radiation here, and it matches. This yellow curve is just showing you how much solar radiation is coming in. So solar radiation, or we're turning the oven on, and then at 12 noon we turn it off. And if you turn your oven off, what happens? It progressively gets cooler and cooler and cooler and cooler and cooler until we can just touch the racks or whatever inside, or the walls of the oven if we're cleaning the oven. Alright. But the degree of hotness or coldness is still in play after we turn the oven off because of terrestrial radiation and some other factors. Alright, so I think I beat that to death, but I want you to be very, very, very clear, because if you're in a check ride and they're like, you may get an examiner who's like, what's terrestrial radiation? Or what's diurnal variation? And, what happens? Alright, we need to understand this. Alright, because let's say we're already at freezing temperatures in the wintertime, and that night we get a forecast for heavy rains, and we're already below freezing. Well, the temperature's not going to do anything but get lower and lower and lower and lower and lower. So for ground operations, we got to pull out salt trucks and salt and urea for runways and stuff like that and everything. And this is why weather is very important, not just for the pilots, but just flight operations in general, dispatchers, any type of coordinators and stuff like that. So, of course, I'm going to plug. So I encourage you all to tell a friend, like, and subscribe. Yeah, of course, I'm going to plug that in. All right. So basically, I beat that to death. The Earth receives. You can read this on your own, but the Earth receives heat during the day by solar radiation, and like I said, but continuously loses heat by terrestrial radiation. So that terrestrial radiation is still radiating that heat. All right. The shape of the Earth causes a geographical variation in the angle of incident solar radiation. And that just goes back to what I talked about. This is the angle of incident, the angle that this solar radiation is striking the Earth's surface. This is striking it as a curved surface, so there's an arc length, if you would, for all my trigonometry guys out there. There's an arc length there. Because you're looking at this is really just a circle as we look at it from a side view. And so the radiation is being distributed over this area. And here, it's more concentrated during the equatorial regions. I can't stress that enough. Alright, so you can pause and you can look at this stuff and go through this on your own. Now, another thing I'd like to bring or draw your attention to is trying to think. Let me look at the temperatures. Okay, let's look at the United States. These are temperature bands. Just think of this as degrees Celsius, and these are temperature bands. So this would be the winter time. Alright, and this goes into the seasonal situation, because what happens is the solar radiation is actually lowered. Okay, so it's more in the northern hemisphere in the summertime. The solar radiation kind of strikes like here as the Earth spins in the summertime. In the wintertime in the northern hemisphere, the solar radiation strikes more or less down here. Okay, so you could literally have a continuous summer if you move from North America to South America, like in the winter months, like say September. If you move down to Argentina or something like that, it'd still be summertime down there in the southern hemisphere. And then when April, May comes around, you fly back home to the U.S. and it in the summer there. So you could actually, if you traveled, you could be in a perpetual state of spring, summer. So this So this would be our winter time. This would be our summertime. Here's the U.S. right there, and this is when the temperature, when in the summertime, when the solar radiation is more concentrated above the equator, and that's because of the tilt. And I did a really good video. Actually, I have a video on astrology, and it talks about the tilt and stuff like that, because it talks about our planets and stuff like that. And so I'm definitely going to have to get back into that. Now, I'm going to pause right here, and we're going to go into temperature variations with topography. So that is part 2 of the weather series. This is Kieno Thomas with Kieno Training Systems. Thanks for watching.